Well, good morning, everyone. My name is Gary Glonek. I'm the Head of Mathematical Sciences at the University of Adelaide, and first of all, I'm very pleased to welcome you to this lecture and also to our campus. I hope you're enjoying looking around our campus despite the weather. It's a wonderful campus and there's lots of interesting things to see and hear. As you know, or you may know, Adelaide is one of Australia's leading universities and indeed one of the world's leading universities. We've been ranked consistently in the top 1% of all universities in the world, and we're really proud of the graduates we produce. We think we produce graduates who not only have a sort of outstanding education to a high standard in whichever field we teach, but we produce graduates that we like to think of as world ready and not just job ready. And we've got a proud tradition, when you look at what some of our graduates have gone on to achieve, of producing people who really are leaders. From the School of Mathematical Sciences, a little known fact is one of our former graduates is actually the President of Singapore. So we do produce leaders and we really produce outstanding graduates. So anyway, I'm not here to talk so much about the university as I am to talk a bit about mathematics. And when I was thinking about this, what I was going to say, I was trying to think about what it might look like to a lot of people in the audience. And if you've been doing mathematics at high school, I know a lot of people will sort of really like the subject just for its intellectual appeal and the beauty of the ideas. But there's also the idea that perhaps it's a little bit theoretical, maybe somehow something that people used to do a long time ago like Latin. And in fact, I really would like to spend some time trying to dispel that myth. Mathematics is really one of the key pillars of knowledge that underpins a lot of what we think is good in the modern world. And I might just go through a few testimonials from some people, most of whom are not mathematicians. So the first one, do more mathematics. This is Sir Gustav Nozzle, who was a distinguished medical scientist. He was the Australian of the Year 2000, and he was the director of the Walter and Eliza Hall Research Institute. For those who don't know, that's a very important medical research institute in Melbourne. What he said was, do as much mathematics and statistics as you can in your degrees. These skills will empower you for your professional life. Here's another one, Ian Chubb. He is Australia's chief scientist, also actually a medical background, but here's what he says about mathematics. He said, mathematics provides the vital underpinning of the knowledge economy, essential in the physical sciences, technology, business, financial services, and areas of ICT. So again, this is what our chief scientist says, and not as a mathematician or as an advocate of mathematics, but as someone who's got a broad view of what's, I guess, especially important, is the knowledge economy, which I think is where the world is heading. Here's another one. It's kind of getting a little bit old, but it's such a good headline. New York Times says statistics is sexy, and in case you're interested, I'm the head of mathematics, but my training is in statistics, so I really like this one. Anyway, there's a guy called Hal Varian who is the chief economist at Google, and he says, I keep saying the sexy job in the next 10 years will be statisticians, and I'm not kidding. New York Times says the rising stature of statisticians who can earn $125,000 at top companies in their first year after getting a doctorate is a byproduct of the recent explosion of digital data. I'll come back to that in a little while, but just to calibrate that, in the United States, when people finish degrees with doctoral qualifications, very often they might be starting on a salary of, say, $50,000 a year, so 125 is seriously good. Here's another one. You live in a mathematical world. The irony of mathematics is that most people seek to avoid the discipline but seek to benefit from what it delivers. Jet planes, broadband, internet, the weather forecast, so many things that contribute to everyday life are the direct result of solving mathematical equations. And one more, this is from Sir David Brown, the chairman of Motorola. Again, for people who aren't aware, Motorola is one of the predominant manufacturers of computing hardware and electronics. Mathematics is a language which transcends national boundaries, cultures, age, scientific fields, industrial sectors and times. If we were to set out to design a language specifically to harness the innovative diversity in our society, it's unlikely we could improve on maths. And the final one I want in this section from the OECD, the search for new life-saving drugs, the development of high-performance materials, and the protection of sensitive ecosystems. All of these application-oriented activities and many others are strongly dependent on fundamental research, and that research is inextricably linked to mathematics. So what do we get from all of this? As I said, if the only maths I'd ever done was high school, I would probably be surprised to hear people in those places saying things like that. Having been around, unfortunately, quite a lot longer than that, I know that that actually mathematics does sort of reach out into all kinds of areas where you just might not expect it. And maybe I'll talk about two examples just quickly. Most recently, I was reading a copy of The New Scientist. I don't know if people ever see that. It's just a sort of friendly magazine on science. But they were talking about a new form of intelligence, and explicitly computer intelligence. Now, everyone uses a computer, I know that, so it's hard not to notice now that whenever you go into anything like Google or Gmail or anything like that, you see advertisements, and these advertisements are getting scarily good at knowing things you might be interested in. Likewise, if you go to something like Google Translate, I don't know if many people have done that, but you find some foreign text you don't understand, you put it into Google Translate, it actually does a really good job of translating it for you. All of this stuff is what's called machine intelligence. And there's this sort of interesting history to it, because maybe 30, 40 years ago, when people really started getting the computers that would give them the ability to try to implement things like computer intelligence, they tried explicitly to write programs that copied the way they believed that people thought about things, and they just turned out to be complicated and not really successful, and the whole area kind of just almost died for a while. Well, recently, companies like Google have got one big difference. They deal with huge amounts of data now, and instead of trying to build machine intelligence that sort of really tried to copy the way the human mind worked, they took a much more pragmatic approach. They said, let's sort of see how we can make sense out of this huge amount of data that's available, and use that to answer things. Guess what the key technology in there is? Mathematical algorithms. Sure, you can't do it without computers and you can't do it without data, but the key difference is that instead of trying to purposefully build something that thought, they just said there's all this information out there, and mathematics is the key tool, the linchpin to getting these extraordinarily successful results. That's where the guy from Google, Hal Varian, was coming from, because a lot of these algorithms sort of trace back to statistical algorithms and then called machine learning and so on, but it's really mathematics is the core technology in that area. The second example I'll talk about is again, not usually associated with mathematics, is the area called bioinformatics. If you think of biology, and maybe it's fun to think in terms of history, if you look back at, go back a few hundred years before the microscope was invented, people trying to study biology and what life meant and how it worked, you'd think without a microscope they couldn't even know there was such a thing as cells, and you'd have to say they were stumbling around in the dark in a sense. These days we've of course gone a long way since then, and one of the big revolutions in modern biology is the ability to understand what's going on at the genetic levels of cells. And this is as they go through various processes associated with life. And one thing this does is create huge amounts of data. Again, it's a similar problem. If you want to actually get the meaning out of the data, and very often people make a distinction between data and information, what you need are well-founded algorithms, and most often the key technology is mathematics. And so for that reason, it's even been said that mathematics is the new microscope of biology. Again, you can imagine looking back in 50 years and saying, well, in the 1990s, before this stuff started happening, biologists were again sort of just looking at the genetic basis of life, more or less stumbling around in the dark. And so there's a really exciting revolution in the way people think about biology that's taking place, and again, mathematics is playing a key role in that. I could spend all of the time this morning talking about other examples of where mathematics has a huge impact, but I do have to move on, and I want to talk about a slightly more practical aspect as well. Here's a testimonial from Bronwyn Hart. She's the chief of the CSIRO Division of Computational Informatics. For people that don't know, CSIRO is the Australian Scientific and Industrial Research Organisation that's funded by the Commonwealth Government. Its mission is really to do scientific and industrial research in the national interest, and the Computational Informatics Division has just been formed from a restructuring. It employs nearly 500 people. Bronwyn said, I had just completed a degree in environmental science and teaching, and also enjoyed mathematics and realised I needed an edge that would help my career. I wondered if there was a career where I could combine the two. I realised the edge I was looking for was the interface between maths and the environment. Well, if you look at where Bronwyn's ended up, I think it's fair to say this has certainly given her an edge in her career. There's not many people get a job like that. So on to jobs, because I know people do think about it. There's a survey in the US about ranking the top jobs, the top professions, and they have a ranking from 1 for the best job to 200 for the worst. I have to say this is it's a bit of fun because it's really difficult to rank jobs, and you can see by the way these numbers move around that they're not all that stable. Nevertheless, it's not only is it fun, but it says mathematics and statistics are really good jobs, so I have to mention it here. So if you look over the years, there are 3 professions I've highlighted. There's something called an actuary, which I'll explain to you if you like. So an actuary is a person who deals with essentially managing sort of probability calculations to do with risk, very often in the context of insurance companies or superannuation and so on. So their job is to actually work out how you should manage your risk in the light of the uncertainty that is exactly the sort of thing that insurance companies and superannuation funds have to deal with. They're inherently a mathematical background, so they do have a lot of mathematical training, and you can see that according to this survey, they were rated as the best job in 2010, the third best in 2011, the second best in 2012, and the first in 2013. This was by this job ranking. The next one is mathematicians. You can see their rankings were 6, 2, 10, and 18, and statistician went 8, 4, 18, and 20. Just a word on what these rankings mean. The methodology they use is they rank each job on about 5 different things. And so some of it is to do with the sort of how physically demanding the work is, some is to do with how stressful the work is, some is to do with the remuneration, and then some is to do with the chances of actually getting a job as well. And you can see that all of these careers, statistician, mathematician, and actuary, actually rate really well. Of course, you're probably wondering what do you think would be the worst job out of 200? Anyone want to guess? Politicians, a good try, but there's actually worse than politicians. The worst job, I think, in 2012 was lumberjack. If you think about it, it's dangerous, it doesn't pay very well, they're not great job prospects, and I think it's stressful too. This year, there's another one joined the shame list, and perhaps not surprisingly when you think of it, is newspaper reporter. Again, it's got all these elements, and although it's got a glamorous image, it's got not much else going for it. So that does raise the question then, well, if you did do a mathematics degree, what sort of job could you get? And this is a point that's worth spending a few minutes talking about, because if you were to pull out the sort of job section of the newspaper or go to Seek and just say find jobs that say mathematician, you're not going to find too many jobs where people say they want to employ mathematicians. On the other hand, if you dig a little bit deeper, what you will find is people working in a lot of areas. So sort of, for example, a lot of biologists will be looking for people to help with their research, and they'll be looking very often for mathematicians or statisticians. If you look up under the word analyst and read the job description of what people are looking for, very often what they're looking for is someone who knows about data, knows about mathematics, and knows about computers. If you look at areas like market research, insurance, banking, again, there'll always be a small number, or a number of jobs there, and not the majority of jobs, because most insurance, and if you look at insurance companies, the vast majority of their workforce are not doing the sort of high-level work that mathematicians do, but the sort of lower-level, or the sort of different level work, perhaps dealing with customers and sort of maintaining policies and so on. But the high-level work, where you actually have big impact and get big bang for your buck, is where you are looking at these sort of more specialised sort of skills that mathematicians and statisticians actually have. And so how would the sort of mathematics and statistics help you? Well, I think, again, maybe a couple of myths to dispel here. The first one is creativity. I know that it's one of the problems with being a statistician is when you get introduced to someone at a party and they ask you what you do, and you say I'm a statistician, they suddenly say, I've just seen someone I know over there. So, and maybe there's a bit of an idea that mathematics and statistics is sort of not terribly imaginative. There's not much room for creativity. That's, again, kind of the opposite of the truth. What these sciences are all about actually sort of understanding the material, but then it's just a way of thinking that does allow you to be creative, to think about problems in new and different ways, and that's why these fields add so much value to so many fields, because part of the training is you do learn to think about things in a sort of mathematical way, and then be able to apply them across a whole broad field of areas and just bring insights that people without these skills simply don't have. Part of this is modelling, so this is, if you think of the power of mathematics as opposed to not having mathematics, imagine that you were trying to do something like design a rocket. If you didn't have ideas of mathematics, you'd be doing it by trial and error. Right, you build one, see if it works, notice that it doesn't, and try building another one, and so on. You go on forever. The whole point of mathematics is that by modelling things, you actually do all the experiments, or a lot of the experiments, by solving equations, and then when you actually get to building ones to test them, you actually already have a good idea that if it's not going to work the first time, at least it's almost going to work. Now that's the sort of mathematical modelling. That's one example, but of course you can apply that in all kinds of ways. Maybe one of the key things, I think, good mathematics graduates are just fantastic problem solvers. And you talk to people in industry and indeed my colleagues in other departments, it's one of the most highly valued things of graduates that you can get, is people want to employ graduates who are able to solve problems. Mathematical training for a good graduate, a lot of them, as I said, are fantastic problem solvers. It's just this ability to learn that you gain from studying mathematics, where you can think about problems and break them down into the sort of simplest parts and solve those, and to just bring in fantastic insights to the sort of bigger issue that you're working on. This is a bit of an advertisement on sort of some tangible results about mathematics. So there's a journal called Science, which is one of the most prestigious and important scientific journals in the world. They did a study in 2007. They showed that taking extra mathematics at high school gave students an advantage across all science subjects. And one of the ones they've said here, and maybe this makes sense in some of my comments, this says including biology, which is a discipline that's generally not associated with mathematics. So what they did was they looked at the performance of college students in the United States and correlated it with the sort of mathematics that the students had done at high school. And what they're saying here is that basically having done extra high school mathematics helps students do well in almost anything they're trying to do at university. Likewise, their second one, they concluded the two pillars supporting college science are basically study at high school in that area of science, and then overall more advanced study of mathematics in high school. Okay, maybe back to the jobs. One of the other things people like doing is forming league tables of how much money graduates can earn. As I said, I've been trying to sort of hopefully give you the idea that although you might not guess there are that many jobs for mathematicians, there are jobs for mathematicians. They're not always called mathematician, and they tend to be fairly well paid. Again, with looking at any profession, you have to sort of trade off a lot of things, but in your salary and potential salary is important. And so here's an indication of where mathematics stands. This was from the Australian Graduate Survey conducted in 2012. So the best paying job for a starting graduate was dentistry, where they start on about $80,000. The overall median salary for mathematicians was $57,000. The overall median salary for all graduates was $52,000. So median, by the way, just means, roughly speaking, half the graduates earn more than that and half earn less. So basically, when you look at graduates altogether, on a sort of half of the fresh graduates who start are earning more than $52,000 and half are earning less than $52,000. For mathematics graduates, it's more like $57,000. And you can see it's surprisingly not very different for the starting salaries for medicine graduates as well. Okay, so School of Mathematical Sciences. Well, what do we have in our school? Our school employs about 35 academic staff, so they are lecturers and professors. And what people do in the university departments is we do teaching and we do research. So you probably have some idea of what's involved with teaching. I'll say more about that in a moment. I'll talk about research first. So research in mathematics involves two possible things. Some of it is about inventing new mathematics that other people might not have thought of previously. And there's, if you look at the history of mathematics, there's always been this cycle of development of new mathematics driven by need. So, for example, differential calculus, which a lot of you will have seen in high school, was really developed in response to people trying to understand how physical systems worked, and it was a whole new branch of mathematics was invented. That cycle just goes on forever because when the differential calculus was established, people got more insight into sort of mechanics of bodies and so forth. They posed new questions that led to new mathematics, and of course, as a byproduct of that, mathematicians got interested in the mathematics they were developing and sometimes developed new sorts of mathematics that just seems so abstract that no one could think of what it was good for. And then a few years down the track, when the technology catches up, again, they decide, well, this bit of mathematics that was invented is just what we need to solve this problem. And it's a growing dynamic field that sort of just keeps going. These days, we have pure mathematicians in our department who are working on areas, I think I've called it geometry because it's too complicated to understand, and quantum field theory. But you look at this mathematics and I have to say it defeats even a lot of people with PhDs in other areas of mathematics. It's just so abstract. But it's exactly the mathematics the theoretical physicists are using to try to understand the very nature of the cosmos, and I'm sure everyone's heard about the sort of search for the Higgs particle and these sort of fantastic experiments with the Large Hadron Collider and so on. And it's that kind of mathematics that people are working on. The second sort of research that we have is, as I've been trying to give you a flavour of, mathematics is immensely useful in a lot of fields, and there's a lot of research done in actually applying mathematics to helping people solve research problems in other fields. And so we've got people working on risk management, econometrics, which is mathematical techniques applied to economics, internet traffic. We've got a very strong group in our department working on how to optimize internet traffic, because internet hasn't existed for all that long. It just sort of sprung up organically without anyone really engineering the internet to make it a robust system. So there's a lot of interest in studying that. We've got people working in climate, nanomechanics, optics, bioinformatics. Bioinformatics is a sort of biology technology I said a bit about before, and hydrology. So we've got a wide range of people working on really interesting things, and I guess today's the day for boasting. We're good at it too. We're rated above world standard in all areas of pure mathematics, applied mathematics and statistics, and we are competitive to the extent we punch above our weight in getting funding to do our research from independent funding bodies. Teaching, I think since I'm boasting, we actually have outstanding teachers in our school as well. We're highly rated in the student course surveys, and there's a survey which hopefully you people will find out about in another 3 or 4 years, which are the course experience questionnaires, which is an exit survey given to students when they leave the university. Again, we scored 96% overall satisfaction rating in the exit survey, which is a really good score. As I said, I hope you'll come and look at the Innova 20 or the Ingani Wardley building, which is our new building. It's a lovely new facility that was built a couple of years ago. And we also have people who are really making innovative use of technology. I better just get down to the final nuts and bolts of this. If you do decide to come and do a degree in mathematical sciences, we offer a number of programs. We've got the Bachelor of Mathematical Sciences and one of the new advanced programs, a Bachelor of Mathematical Sciences Advanced, which is restricted to students with a 95 ATAR. We've already had some outstanding students in there. And we also had the Bachelor of Mathematical and Computer Sciences. That's one of our long-standing degrees where you can do mathematics or computer science and a little bit of both. But one of the really great strengths of that degree is that it's available in a lot of double degree combinations, and people use it to reinforce their studies in other areas. We also offer some graduate programs, so we have a master's degree in mathematics and also a PhD degree. But anyway, let's not get ahead of ourselves with that. So just to finish off then, if you want to get more information, please drop into the atrium of the Ingani Wardley building this morning. There's lots of interesting things and people there from all over the Faculty of Engineering, Computer and Mathematical Sciences. And also I'll hang around for a few minutes afterwards if anyone wants to say anything. So thank you very much for your attention and enjoy the rest of your day.